here we go. All right, gentlemen, this class recording has started. So, yesterday, first let me move this out of the way. Yesterday, we began our discussion of ionic bonding, and we said that at its core, or when you break it down, why does ionic bonding happen? Maya, go ahead. Why is 8 valence electrons important? Yeah, there's something else I'm going for. It is, what did you say? Stable, or it is a, something is stable because it has what? Or it doesn't have what? Nope. Sorry. First thing we wrote down yesterday, or actually the second thing we wrote down yesterday. Bonding is what kind of a process, or involves what? Energy, right? At its core, bonding happens because atoms have less energy when they are bonded with each other than they do when they are separate from each other. Okay? Now, Maya, we got into then, what does that mean? Well, it means 8 valence electrons, full outer shell, that kind of stuff, right? But those all are just indicators of something that has a low energy. Okay? All right, so yesterday we started talking about Lewis structures. What does a Lewis structure show us? Okay, good. Number of valence electrons, right? It's just a picture that has the symbol of that element and dots that represent its valence electrons. Where do we look to determine how many valence electrons an atom has? Well, how do we know how many electrons are in there? Yeah, so where we look? Look on your periodic table, right? Depending on what group it's in, that will determine how many, or that will tell you how many valence electrons it has, right? Group 1, sorry, pull this up, right? Come on, web elements. There we go. All right, so, right, based on its location on the periodic table, that will tell us how many valence electrons it has, right? Group 1 has 1 valence electron. Group 2 has 2 valence electrons. We basically said we're going to skip over our transition elements, so all the pink and the green ones on this are on this periodic table. And we pick it up here at 13, 3, 4, 5, 6, 7, 8. Okay? We said that magic number as far as valence electrons concerned is 8, right? Full valence shell. Some elements already have 8 valence electrons, and as a result, what kind of properties do they have, or what's one of their properties? They are unreactive. They don't react or form compounds with other elements because they don't need to. They are already in a low energy state, right, with their 8 valence electrons, so they don't need to go anywhere. Good with that stuff so far? Okay, go ahead. That is basically what bonding is about, right? Bonding is about, if this tennis ball represents an atom, right? When we hold it up in the air, it's a high energy state, potential energy, right? If we let it go, what'll happen to it? It'll fall, because what happens to its potential energy as it falls? Decreases. That's why these atoms trade electrons basically to get to that low energy state. That 8 valence electrons is the equivalent of the tennis ball sitting on the table. It is a low energy state, and it will stay there as long as it can unless we make something else happen. Okay? Does that make sense, Kate? I mean, that's pretty much what the gist of it is, right? Trying to make that comparison between chemical energy and gravitational potential energy. Okay? All right. Yesterday, I believe we left it off here. Is that correct? Okay, so talking about how does this actually happen. So, on page 2 of your outline, I believe it's Roman numeral number 4, it says, how does the bond between sodium and chlorine form? Is that correct? Okay. All right, so we started off drawing our Lewis structures. Sodium, 1 valence electron because it's in group 1. Chlorine, 7 valence electrons because it's in group 17. Did we get these two things written down? I can't remember if we got that far or not. Okay, so sodium, 1 valence electron, is looking to lose it. Chlorine, 7 valence electrons, is looking to gain 1. This is a very mutually advantageous situation, right? Sodium's looking to get rid of this electron. Chlorine needs to pick one up. And we said, right, magically, that happens. Yes? Woo! Right? Yep. So, I mean, it's animation at its best right there. I mean, it's just like, there's like, you know, Toy Story and Frozen and then this. That's like the order of best animations ever. That's, you know, so, yeah. Anyway, so let's talk a little bit about what occurs when this happens. All right. Metals form cations, not cations. Okay? So, metals. So this is on Roman numeral 4, letter B, I believe. Okay? Metals lose their valence electrons to form cations. All right? Again, not cations, cations. One of the things that we stressed back in Unit 3 when we were talking about atomic structure was what is true of the number of protons and electrons in an atom. They're the same, and it's always in numerically equal to what on the periodic table? The atomic number. But if we start moving electrons around from one atom to another, now those atoms do not have an equal number of protons and electrons. When metals start losing their electrons, they end up with more protons than electrons. So they have a positive charge, because protons are positive and electrons are negative, right? When that happens, we refer to them not as atoms anymore, but as cations. Atoms have equal numbers of protons and electrons. Cations do not. Okay? On the other hand, nonmetals will look to gain electrons. When that happens, they have more electrons than protons. And they become anions, not anions. They're not the cousin of onions. Anions, no. Anions. Okay? So, atoms have equal number of protons and electrons. An atom that does not have an equal number of protons and electrons is no longer an atom, but is called now an ion. Ions have unbalanced protons and electrons. Specifically, cations have more protons than electrons. Anions have more electrons than protons. But in general, we refer to them as ions. Okay? Good with the terminology so far. Okay? All right. Let's apply it back to our situation. After we have transferred this electron from sodium to chlorine, okay? After the electron has been transferred, remember, sodium's trying to get rid of that electron, chlorine's trying to pick it up. But after it has been transferred, okay, sodium now has 11 protons, but only 10 electrons. How do I know sodium has 11 protons? That's its atomic number, right? And it started with 11 electrons, but one of those electrons went over to chlorine. So if sodium has 11 protons, but only 10 electrons, that means it has a positive charge. We call that a cation. If you flip it over to the third page of your outline, this stuff shows up on the third page of your outline. So. But on the other hand, chlorine now has 17 protons, but it has 18 electrons. And I know chlorine has 17 protons because that's what? That's its atomic number. So chlorine now has 17 protons, but 18 electrons. It now has a negative charge because it has more electrons than protons. And so it is now an anion. Julie, go ahead.
How do you know which elements have more protons and
So, the last couple screens that we just looked at, right, Julia, we said that metals generally have low numbers of valence electrons, okay? If we look on our periodic table, right, metals are over on the left-hand side, okay? So column 1, we know has one valence, all these have one valence electron. Column 2 has 2 valence electrons. These have 3 valence electrons, okay? We said that 8 is the magic number, but we could either gain or lose to get to 8. Elements that have 1, 2, or 3 valence electrons will generally lose those valence electrons because it's easier to get to 8 that way than it is to gain more. But group 15, 16, 17, 5 valence electrons, 6 valence electrons, 7 valence electrons, it's easier for them to pick up electrons. Okay? So, general rule. Metals, left-hand side of the periodic table, will tend to lose valence electrons. Non-metals, right-hand side of the periodic table, tend to gain valence electrons. If you're losing valence electrons, you end up with more what than what? If you're losing electrons, you end up with more protons than electrons. But if you're gaining electrons, you end up with more electrons than protons, right? If you've got more protons than electrons, what charge are you going to have? And if you have more electrons than protons, what charge are you going to have? Negative. Does that make sense?
Yeah, so if they have 3 or less electrons, then
3 or less, you're generally going to lose them. 5 or more, you're going to gain.
okay.
And that means that metals lose electrons, non-metals gain
What
electrons.
about 4?
Let's not worry about 4 right now. Let's wait until next week to talk about that. Okay? Different kind of bonding. Right? Are we okay with that for now? Okay. So, right, the magic has not passed just yet, everybody. Okay? So, sodium has 11 protons, 10 electrons, positive charge. Chlorine, 17 protons, 18 electrons, negative charge. What do positive and negatively charged things do? Okay? I mean, Toy Story 2 was pretty much as good as Toy Story 1. That was pretty much as good as the previous animation. I mean, let's face it, that was top quality. That was like PowerPoint 2005 kind of quality right there. So the negative charge on the chlorine anion and the positive charge on the sodium cation attract each other and form an ionic bond. It is an ionic bond because it exists between 2 what? What do we call those things that have different number of protons and electrons? Ions. That's why it's an ionic bond. It exists between 2 ions. Okay? Good there? All right. Let's talk about ionic bonding in general. Okay? So, just as negative charges are attracted to positive charges, negative anions are attracted to positive cations, and vice versa. And if you look at the very first thing we wrote down on this outline, the very first thing that we wrote down was what? A chemical bond is a what? Attractive force that holds atoms together. There it is, right? An ionic bond is an attraction of opposite charges, or oppositely charged ions, if you want to write it that way. Ionic bonds happen after the transfer of electrons from a metal to a nonmetal. Right, Julia, we said that metals are losing electrons, nonmetals are gaining electrons, so electrons go from metals to nonmetals. When that happens, now one's positive and one's negative, and they attract each other. All right, good here. Okay. Question, Katie. There are multiple ways that atoms can be held together by attractive forces. This is one way. Okay. Next week we're going to talk about covalent bonding, which is a different way of attracting atoms together. This is one form of bonding. Bonding in general involves the attraction of atoms. This is one form. Okay. All right. Good there? Okay. On your outline, you have the back of the last page completely blank. Okay? There's a couple of examples that I wanted to do here to kind of just get us back or make sure we understand how this applies, different situations and stuff like that. Okay? And then we'll sort of preview what you guys are going to do tomorrow in class as well. Okay? You guys don't have these examples on the back of the sheet. I'm just going to show them to you up here, so you write down as much or as little as you would like. Okay? All right, we good with this? Everybody got this filled in? Okay, here's what we're going to do. We are going to start with the example of bonding between potassium and iodine. Okay? So, over here, right? There we go. All right, so we're going to do potassium and iodine. So first, let's start off with Lewis structures. In order to draw a Lewis structure, we need to know what about an atom? How many what? Valence electrons. So first you got to find potassium and iodine on your periodic table. Okay? All right. Have we found potassium iodine in the periodic table? Potassium, what group is it in? Group 1, and that means how many valence electrons does it have? 1. So, Lewis structure, right? Looks like that. Iodine, what group is it on the periodic table? 17, that means it is a what? What do we call that group? Remember what group 17 is called on the periodic table? It's a halogen, okay? So, but more importantly for this discussion, how many valence electrons does iodine have? 7, right? So its Lewis structure is going to look like this. 1, 2, 3, 4, 5, 6, 7. All right? Good there. Julia, which one is the metal, potassium or iodine? Potassium. And that means what is potassium looking to do with that electron? Give it away. That means iodine is what? First, it is a metal or non-metal? Non-metal, and that means it's looking to what? Gain electrons, right? And that means we have a real nice convenient situation where this happens, right? All right, let's answer some of these questions here. Okay, I know you guys don't have these questions, but let's answer them, right? So, what element is forming the cation in this situation? Okay, Potassium, because cations end up with more what than what? First off, cations have what charge? Positive, and that means they end up with more what than what? Protons than electrons. So potassium forms the cation. Now, symbol. After the transfer of this electrons, or this electron, how many protons does potassium have? After the transfer of the electron, how many protons does potassium have? Done. 19, because that's potassium's atomic number. But how many electrons does it have now? Only 18, okay? So it has one more proton than electron, right? We represent that like this, okay? First we write the symbol, and then as a superscript, we'll write what charge it has and how different the protons and the electrons are, okay? You could write it +1, or you could write it 1+. Really doesn't matter. If you really just don't like writing 1+ and you'd rather write +1, that's fine too, okay? But this represents our potassium cation, okay? Good there. And then that means which element is going to form our anion? Iodine, that's not a hard choice. You only got one thing left, right? Okay. And its symbol, right? First we're going to write its chemical symbol. How many protons does this iodine anion have? How many protons does this iodine anion have? 53. But how many electrons does it have? 54. Okay? This is not an actual number, it's just the difference between protons and electrons. So in this case here, we would write 1 minus, because it has one more electron than proton. Yeah, it has a lot more electrons than potassium does, but that's not important. All that matters is how different they are. Okay? Good there. All right, now let's take care of this last column here, right? So, the formula for a compound tells us about what atoms have been bonded together. Okay? So, potassium is looking to lose 1 electron. Iodine is looking to gain 1 electron. So it transfers that electron from here to here. Is everybody happy after that transfer of electrons? Or that transfer of electron, I should say. Yep. Potassium's got its 8. Iodine's got it 8. It's a lot of possessives and non-possessives. And yeah. Iodine has 8. Potassium has 8. Everybody's happy, right? So, to get everybody good with their 8 valence electrons, we need 1 potassium and 1 iodine. We represent that like this. First, we write the symbols of the 2 elements. Metal always comes first. Okay? That's just a rule you got to learn. Metals come first. So, potassium first. Iodine, so you like metals before non-metals?
No, it just sounds better. Like
Yeah.
potassium iodine or iodine.
That's just because you're probably used to it, right? And also M becomes before N, so if you think about it that way, metal versus non-metal, you can think about it that way, right? And then we may or may not need some subscripts here to tell us how many atoms. In this case, it's 1-to-1 ratio, so we just leave it like this. Okay? Technically, yes, it would be wrong. No, not even technically. Yeah, it's wrong. How's that? So, how about this? This is what you really want to know. If you put it on a test, I'm marking it wrong. How's that? Okay. Is that words you can understand? Is that I'm speaking your language now? Is that, all right, name-wise, the name of this compound, representing atoms that are bonded together, just comes from the names of the two elements. So first, it's two words. The first word is the name of the metal. The second word is the name of the nonmetal, except we change the ending to the IDE. Okay? You only change the ending of the nonmetal, though, not the metal. It's not potassiumide iodide. Okay? Potassium iodide. Okay? Good with that for starters. It's actually, yeah, a lot of it, when sometimes when your salt is iodized, you get iodized salt, this, a little bit of it, it's very similar to sodium chloride, so, because if you look, potassium and sodium are in the same group on the periodic table, chlorine and iodine are on the same group on the periodic table, they're going to be similar, so. Okay, go ahead. Sure. Okay, so that's a good question. So Kate asked, right here, this is happy because potassium has 8 valence electrons, okay? But what if we do something like lithium, okay? So let's do that. Okay. Okay, there's the electron configuration for lithium, yes? I actually skipped over this a little bit. This is actually in your outline. Actually, I skipped over it a little bit, okay? So there's the electron configuration for lithium, yes? 1s2, 2s1. And that means how many valence electrons does it have? 1, right? Because the highest level is number 1, and it only has, the highest level is the second energy level. There's only 1 electron in it, okay? If it loses that electron, this will be all that's left. So how many valence electrons would it have then? Technically only 2. However, right? Maya, before we said that you kind of told us that the intent of bonding is for atoms to get what? A full shell, right? A lot of times that's 8. But, Kate, when we're talking about this shell, right, the first shell, remember there are no p orbitals or d orbitals in the first shell. There's only an s orbital. So this shell is full with only 2. So it doesn't have 8, but it does have a full shell. So when we're talking about lithium, or when we're talking about hydrogen, or when we're talking about helium, right? Helium is a noble gas, but it only has 2 valence electrons. It still doesn't form bonds, though, because that's full. All right? Does that make sense? So if you look actually at the bottom of page 2, bottom of page 1 or top of page 2, there might be some questions there that says, does this always mean 8 electrons? Is it maybe the top of page 2 of your outline? Let me see here. I'll tell you. Yeah. Okay, yeah, exceptions for smaller ones, right? The important part is more that the highest energy level is full. For small atoms, that could only mean 2 electrons because the 1s only needs 2 to get full. Does that make sense? So yeah, it's 8 most of the time, but for small atoms, it can be 2. Okay? Good there. Okay? All right, let's do this. Going back to practicing a little bit more, let's go here. Okay? So if you were writing this on the back of your outline, this might be a good place to pick up the next one. Okay? All right, bromine and calcium. Okay? Find them on the periodic table, because that's got to be first. And as you find them on the periodic table, if you want to draw their Lewis structures, you can. check. Lewis structures for both of them are up on the board. Okay. So calcium is in group 2. It has, by the way, where you draw the dots is not as important as if you have the right number of dots, okay? So if your dots are not in exactly the same place as mine, that's okay, as long as the numbers are right, okay? So, calcium, group 2, 2 valence electrons. Bromine, group 7, 17, 7 valence electrons. Yep, good there? Okay, so, Julia, which one's the metal, which one's the non-metal? Calcium's the metal, so it's going to look to do what? Lose electrons, right? Specifically how many? 2. So, this is going to happen first. Okay? All right, once that happens, is bromine good? Bromine's good. Is calcium good? No. Calcium's got 1 valence electron now. Does calcium like having 1 valence electron? Nope. Didn't like having 2. It's not going to like having 1. Okay? But can this bromine atom help it out anymore? Nope. So what does it need? Needs something else, right? It would be nice and convenient if, say, another bromine atom came along, right? With its 7 valence electrons, because this bromine atom is looking to do what? Gain how many? 1. This calcium atom just so happens to have another one that it needs to get rid of. Oh, look at that. Everybody's happy now, right? Okay? So, let's answer these questions in the middle, right? Which element is forming the cation in this group? Calcium, because it is losing electrons. But, different than before. How many electrons does it have to lose? 2. Meaning that it starts with, it has how many protons? Look on your periodic table. How many protons does calcium have? 20. But now, how many electrons does it have? Only 18. So, symbol, is it going to have a positive charge or a negative charge? Positive, but positive how many? 2 plus. Okay? Bromine, though, each bromine atom only gains what? How many electrons? 1. So, it's still -1. Okay? Formula-wise, to make everybody happy, how many atoms do we need? We actually need 3 atoms. How many calciums? Only 1, but how many bromines? 2. So we represent that in the formula like this. First, which symbol comes first? Metal always comes first. Calcium. Non-metal comes second. Bromine. But, oh, you're not done. Throw it back there anyway. Just so I know. But how many bromines do we need? We show that with the subscript. Okay? Here, these superscripts we use for charges. These subscript we use for how many of each element we need, or how many of each atom we need. Okay? Name. Start with the metal. Calcium. Second word. Bromide. Oh my goodness gracious. Okay? There is some homework on the calendar for this evening. It involves some reading and then a couple of problems from the book. All right? Just kind of general stuff. Tomorrow we will continue working on formulas and names. Bring a book tomorrow, please.